Not correct. I'll give the better diagram. Okay, there's a rectangular cross-sectional toroid of iitj shaped like this. Very important and can be asked such things in exam. So toroid, can you remember Ampere's circuit law? We have discussed toroid. There the cross-section was circular. Here the cross-section is a rectangular. This will be rectangular. So the small gap will be there here to make the diagram. I'm making things visible. So here these are the turns. Okay, no. This side view. Of inner radius A, outer radius B, and this is the yellow color one. Okay, carry on. A small gap, we have to show it. Hope if you can remember, directly let n be the number of turns. Go back to Ampere's circuit law and get that formula for magnetic field inside this toroid. Once you know magnetic field, then we can go for self-inductance like previous problem. Let n be the number of turns, inner radii A, outer radii B. Or the magnetic lines of force. So let's assume that current here. Current here. So let me send a current I here. A current I will flow. So it will produce a magnetic field. This magnetic field lines, I'll show it, circular one. I can show only 2 or 3 lines. Small narrow gap it is. Very small narrow gap it is. In fact, should not also be there to make you explain what I just brought it here. I think, okay, the gap should not be. Let's remove gap. Again, you'll start thinking some other way. Yeah, carry on now. So the lines of force will be in this direction. What is the expression for B bar? First of all, B bar. Anybody? We discussed, no? The value. B bar at a distance R. So what I do is like I'm going to assume a DL here. B bar dot DL equal to mu naught N into I, no? Why N into I? So these many terms, 1, 2, 3, 4, 5, here is what the Amperian loop is assumed. So how many turns are enclosed? 1, 2, 3, 4, 5, 6, 7, 8. So N I's are enclosed here. So this will become B bar into DL mu naught Ni. 2 pi R mu naught Ni. Look at the magnetic field. In fact, the magnetic field is variable here. If B is very much greater than A, then it will remain constant. Okay, no, the B is variable here. So I am going to assume now here a strip. Height of the strip already given H. Let it be dr. So what is the flux linking this strip is what? We'll calculate here. So d phi is equal to B into dA. B into what is dA? H into dr. B is equal to mu naught Ni 2 pi R H dr. Mu naught NH I 2 pi dr by R. Just from college, a call is there. Meanwhile, you finish off. I'll attend that call. What should be the limit? Limit should be from A to B. So solving this, flux equal to mu naught NH by 2 pi I log of B by E, self-inductance. Widely used in plenty of applications. You may encounter any of structure, like how to find out the resistance of various shaped structures, how to calculate the capacitance of various structures. Like that also, self-inductance of different current carrying structures can be asked for you in exam. Now we'll go back to, so this is about, we'll go to the some numericals on mutual inductance. Once again, we'll go back. So there are plenty of different ideas are there, which I wanted to share. This will be very useful for you in exam. What I'm going to discuss, the mutual inductance ideas. Let's go for the application. So the first one will start. So I'll begin with a very simple. Let there be a long wire.